All right, so the first thing we wanted to define was the initial point, which is really just the start of the vector, right? The starting point of the vector. And the terminal point is just the ending point of the vector, right? Like, start versus end. So really, really simple explanations here. So this is where the vector starts. And the end here, you'll have another point, and that's where it ends. So in the figure B, each of these vectors are equivalent. What does that mean exactly? So the exact answer for this is for them to be equivalent, they have to have the same magnitude and direction. So, if you said they have to be the same length, then they have to be parallel, or they have the same slope, those things are not wrong because they do indicate direction. And the magnitude is just the length of the vector. But in general, this is your exact definition. For them to be equivalent, they have to have the same magnitude and direction. And of course, all of these do. They're the same length from the starting to the initial point, and they're all parallel. They all have the same slope. They're all going in the same direction. We haven't formalized how to indicate direction yet. That'll be done with an angle. We'll talk about that probably tomorrow. So, okay, the magnitude of the vector is the distance between the initial and terminal point. So, how can we calculate the magnitude? Well, you can use the distance formula. I mean, if you want, that's perfectly fine if you don't have, a grid or something. Or you can use the Pythagorean theorem, which to get the distance formula, we actually just mess with the Pythagorean theorem a little bit. This comes from this anyway. That's why it looks so similar. So for these, let's do a couple of these, and I'll do this one, right? So it says to calculate the magnitude of each vector. Well, if I'm going to use the Pythagorean theorem, then I'm going to construct a right triangle because the Pythagorean theorem only works on a right triangle. This is a length of 4. This is a length of 6. And so these are the A and B values for your right triangle. This will be 6 squared plus 4 squared equals C squared, which really ends up being, if you want to put it all in your calculator at once, the length of the vector. The length of your vector is just the square root of 6 squared plus 4 squared. It should be 2 root 13. And a little bit of notation for you. We denote the vector AB. Let me show you kind of over here to the side. The vector AB is written like this. AB with this kind of half arrow on top of it. This is the vector AB. And then the magnitude of that has another notation. And it's done with double absolute value bars. So if you see this, we read this, the magnitude of the vector AB. So that's what this is. This is the magnitude of AB. Double absolute value bars. But that's how that's found, right? We use these components. These are called the components of the vector. This is the horizontal component. And this is the vertical component. And then this is the vector itself, which has a magnitude and a direction. Okay, so you can find the same thing with these two, doing the exact same thing. We'll skip that for now. Are any of the above vectors equivalent? No, because they do not have what is required for equivalent vectors, which is the same direction and magnitude. They don't have the same direction and magnitude. So that's critical. If I ask you, are they equivalent, they will have to have this and this, both of those things to be equivalent. The only thing that doesn't matter is the location of the initial point, right? It can move around. Okay, so of the above vectors, only EF is in the standard position. That's this one. The standard position is when the initial point is located at the origin. So if you have anything other than that, make sure you edit your answer. The initial point is at 0, 0. And that actually makes things really, really easy. So we really like these to be in the standard position. Okay. So then it asked me to draw a vector on the grid above that is equivalent to AB, but is in the standard position. And I'm going to show you in blue. So here's AB, and this is the equivalent vector in the standard position. Notice it has the same horizontal and vertical components of 6 and 4. Therefore, obviously, the magnitude is going to be the same because you use the same numbers in the Pythagorean theorem, except the initial point is now located at 0, 0. And what's convenient to notice is that, what's the terminal point of this guy? Well, it's, 12, 10, which by itself doesn't give me any information about this 6 and 4. But the terminal point in the standard position is actually 6, 4, which definitely tells me something about the components. Okay, so if it's located at 0, 0, the terminal point by itself tells me the lengths of the component sides. That's why I want them at 0, 0. This doesn't tell me anything about that. So, I guess that should be 8. That's not bad. Well, it's cool. It happens all the time. All right. Without drawing the vector on the grid, where would the terminal point for CD be if it was in the standard position? So this would actually, if this was 0, 0, to get to the terminal point, I would go over 4 and down 4. So that would actually be, 4, negative 4. Well, how can we find the terminal point of the vector in standard position? Well, yeah, I mean, it's literally just the point. I don't like that question. It seems redundant and confusing. It's the terminal point and the vector in standard positioning component form are the same thing. So let's talk about that down here. The vector whose initial point is the origin can be uniquely represented by the coordinates of its terminal point, which we saw up here. Right? 6, 4 perfectly describes this vector. The component form, this is important, can be written as V1, V2, but it's got these sharp, less than, equal than looking signs instead of the parentheses, where this is the horizontal change, just like the X, and this is the vertical change, just like the Y. So here we have this vector, and AB is its component form. So this is the vector AB. So notice that the horizontal change, you go over A units. See right here? A. And then here you go up B units. So you can describe this as a vector in component form. Or if we count, A is equal to 4 and B is equal to 3, right? So we could also describe this vector as 4, 3. And its terminal point is the point 4, 3. So the component form is just the terminal point of the initial point being at 0, 0. That's it.
And so when we write terminal points, we have to do
This is the terminal point. So all coordinates and points are done with these nice parentheses. Mm-hmm. This is a vector. Okay. This is a vector that is described by its terminal point. And that's a small distinction. But a vector is this whole thing. This arrow here is the vector. This is the point. Okay. This describes basically any vector that has a horizontal change of 4 and a vertical change of 3. No matter where you move it around, it's still the same vector. As you noticed in your car exploration, it didn't matter where the blue arrow was. All it mattered is how long and in what direction it was pointing. It's just convenient to put it at 0, 0 when we're calculating. All right, so this one says graph the vector in component form. This is a vector and it is described by its terminal point, which is 4, 7. So that's 4, 7. But the actual vector is this. So this is vector V, also known as vector 4, 7 in component form. Again, the horizontal component of the vector, as we saw before, is 4, and the vertical component of the vector is 7. I mean, it's pretty easy to find the magnitude at this point. It's the square root of 4 squared plus 7 squared, just using the Pythagorean theorem. It's a nice shortcut to know if you don't have a grid. If I just give you this, you can just use the Pythagorean theorem on this. 4 squared plus 7 squared. So this is root 65. And the way we would write this magnitude is we would write the magnitude of vector V is equal to root 65. Or if you're approximating with decimals, that's fine also. All right. How can the magnitude of the vector in component form be found for any vector? Well, if you have some vector A, B, right, let's say we have vector V defined to be A, B in component form. Well, the magnitude of vector V is just the square root of A squared plus B squared. Just do the Pythagorean theorem on it. All this means is the magnitude or the length of the vector V. Or let me give you another example. Let's say I have some vector U defined to be, P and Q for its terminal point. The magnitude of the vector U would just be the square root of P squared plus Q squared. Just take those two numbers and plug them into the Pythagorean theorem. By definition, they're going to be your horizontal and vertical components. All right, this is a nice one. Find the component form and magnitude of the vector that has initial point 4, negative 7. That's going to be what? About right here. And negative 1, 5. So that's a vector that it's ugly, but whatever. It's cool. All right, so if we go ahead and start off here, let's you can't find the component form yet, but we can find this. So this will be 12 and this will be 5. So the horizontal change from the initial to the terminal point is 5 and 12. Okay, so what's the magnitude? Well, it's 5 squared plus 12 squared, which will be 13. So the magnitude of the vector is 13. And check it out, the component form is negative 5, 12. What? 5, 12, 13 is a Pythagorean triple. Well, you can plug that in your calculator and you'll get the same thing. Y'all are laughing. Ask me some questions. There are no stupid questions. No questions?
How do you know how far to go over?
Well, because we have an initial point and a terminal point. Right? So you can think of it as the same process that we use to find like the slope or something. But this is that same triangle that I just got done doing multiple times in the beginning of the exploration, from the initial point to the terminal point. And look, if I shifted this into the standard position, like I go over 4 and I go up, 7 or something, you would just move that whole vector up. So this is 13 over here. Why is this negative?
Oh, because you're going to the left.
Yeah, that went left. If I'm looking for the terminal point, like in this up here somewhere, I'm going to go left and then up. this has been moved over here to the 0, 0 point to make it up in the standard position. Okie dokie. So it might be useful, yes, ma'am.
So if you switch the initial point and the terminal point, like if it started at -1.5 and then it ended at the bottom point, would you do -12 or would it just stay 12?
Well, you would go down then. So it'd be -12, +5. Yep.
Okay.
Yep. Because then your initial point would be down here somewhere, right? Yeah. Okay. So if we just in general are looking for the way to find the component form of any vector with any initial point, any terminal point, remember, how do we do this if it's in standard form? What's the terminal point of this vector? And that's the initial point.
4, 7.
Yeah, so the initial point here and the terminal is 4, 7. Now, coming down here, can you tell from this number where the initial point and the terminal point are? Look, it's not obvious, right? Because it's not in the standard position. However, there is a formula that we can use. So if you take your terminal point and subtract the initial point, it will give you the component form in the standard position. So basically what that looks like, let's see if it works. So that would be -1 minus 4, comma, 5 minus -7. Does that give me this? Yeah. This would be -5. 5 plus 7 is 12. So instead of having to do all this rigmarole of the counting with the triangle, you can just subtract those points. So if this is the terminal, U1 minus V1, and then U2 minus V2 will give you the component form of the vector. And all this is the horizontal change. And this is the vertical change. Which, I mean, is exactly what we see here. This is the horizontal change, which we saw to be -5, comma, the vertical change, which we saw to be 12. This just gives it to me without having to look at the graph. If you have initial point x1, y1, and terminal point x2, y2, this formula looks like this. x2 minus x1, comma, y2 minus y1, which is a little more familiar. This is the horizontal change, and this is the vertical change. Either way works. Okie dokie. I'm gonna let y'all work on your stuff. You got like 20 minutes. The first two just ask you to put checks in the boxes next to the ones that answer the question. It says, what is a vector? And it gives you a list. Just check what works. Y'all keep your exploration. This that I'm giving you now is due when you get here tomorrow. One more small piece of information, and you're gonna ask me about it, so make sure you're listening. Just like with your exploration, the grid didn't print on your paper for number 4, but it's in classroom if you need to look at it. I don't know why I didn't print, I guess it was just too late. But it is in there for you, so I'll show you what I mean, if you're not sure. On number 4, you have the slowest computer on the planet sometime.
Miss Apple.
Yes.
Is it just like multiple choice?
So in the first part, in numbers 1 and 2, you're given check boxes.
Oh, like, okay.
And so you'll answer all check boxes that I'm being snarky because I said that just a second ago. But yeah, you'll just check the ones that answer the question. So here you go. See how you can't see that grid on your paper? You can look at it there. And it's in Classroom if you need to pull it too. I think on the back it's good. No, the back's trash too. The numbers are there for you though. Apparently the printer doesn't pick up the blue for some reason. Lame.